Hello everyone, my name is Chen. I'm a statistician working at Scientific and Statistic Computation Core, and I manage the Athens software for brain image data analysis. So I was given this talk, minimizing information waste by Peter Bonadini, so I had to think about what I would like to cover this topic. So I'm going to focus on three stages during the fMRI data analysis pipeline. So whenever we have an experiment, we start with the first stage, design the experiment. Then we collect the data, right? So data is basically motor signal. Then we go through some pre-processing steps. Then when the data is ready, we put that into a model, actually probably multiple models. And in the end, we report the results, right? So those four components. So I consider that they are relevant from modeling perspective. First, the design, so that is crucial. Then we have the input. The input basically is the data. Then we have, consider the modeling part is basically the data machine, right? So once we have the input, the data, and we put the data into the machine, we do a bunch of things, then we have the end product, which is the output. So those are the four components. So those four components are related to some extent, but since this is fMRI data analysis is a complicated process, right? So it's multidisciplinary, involve probably a team with multiple members. So usually, in real practice, it's to some extent very disconnect. That may have some issues from modeling perspective, right? So usually we say the output, right? So the statistical modeling output, then usually the paper, right? Paper is the ultimate goal, but that goal, to achieve that goal is a complicated process, and sometimes because the disconnectedness, we may run into some issues. So let's talk about, since I'm a statistician, I want to focus on the statistics. You may think in fMRI, the statistic plays a dominant role because in common practice, the p-value is important, right? So that determines what you kind of report, right? So if you look at it with the papers, you see those figures, tables, especially the figures, you see the color bar. The color bar either the t statistic, z statistic, or p-value. So those, basically that's the important part, right? So that the threshold, that threshold is basically cut off. So anything above the threshold, usually you are allowed to report. Anything below the threshold, then you're not allowed to show that in the paper. And even when you construct a model, what kind of variables you want to put into a model, that's sometimes in traditional statistics based on how important those variables are. I mean, how to measure the importance of each variable. Sometimes people use the p-value, or sometimes use the r-squared, the determination coefficient, that determine the importance of each variable. So those you may consider statistics is pretty much play a role of a gatekeeper, right? But there are problems, right? So we may think, why do we heavily rely on statistics to make a decision on what can we report, what we cannot? There are other information other than just statistics. For example, brain regions. Based on previous studies, there may be some cumulative knowledge about the involvement of some brain regions. Can we use those pieces of information, right? The brain have structures, right? So we know most of our regions, are bilateral, they're bilateral symmetry. Can we use that information to support our statistical evidence, right? So there are variables, there are causal relationships. When we build a model, do we need to consider those causal relationships? What do we mean? What do I mean by causal relationship? Right, so those are the issues we need to consider. So those four components, let's start with the first one, experiment design. So fMRI, pretty much focus on fMRI, but there are other like EGM, EEG, right? MRI, we have three types. Top task related. So that means you ask the participant in the scanner to perform some tasks, right? To say something, do something, right? A bunch of things. So that's task related. Or you can, another public drawing is called a resting state. So the participant just lies in the scanner doing nothing, right? Either keep eyes open or closed. So resting state, there's no manipulation, unlike task-related experiments. So that's called a resting state. In between, there's a called naturalistic scanning. That means usually watch a movie or listen to something, right? Listen to a talk or music. So that's, you do have some sort of a manipulation, but also it's like not, people like natural scanning because unlike the typical task-based learning experiments, the tasks pretty simple, right? It'll be far away from real-life experience, right? So like push a button, say some side face, it's so different from the real life. We walk on the street, right? So that's, or interact with your friends. So that kind of experience is different from the simple tasks in the fMRI experiment. So the naturalist scanning is considered a little bit more realistic, closer to real life experience. So that's why some people prefer to scan subjects in that context. So those are the three basic types. So that's from the experiment type. Then there are many other parameters. The scanner have some parameters. So the TR, spatial resolution, right, flip angles, etc., etc. So here, from statistical modeling perspective, what do we care about is number of participants. That's like one type of sample size. Then you have some number of conditions, right? Like side versus happy. So those are two conditions. So what kind of conditions you want to design an experiment? Then there's a concept of trials. Each condition will need some number of trials, not just one trial, right? Like happy face. Suppose we put 20 different types of happy faces or side faces, not just one. Because whenever we do statistics, we need some repeated samples to give some reliable measures. So those are the experiment design parameters. In traditional statistics, we think about how many samples we need to consider, right? So for fMRI, most of the time, people focus on number of participants. That's the major sample size. So do we do power analysis to determine how many participants we should require to achieve some power, right? So power traditional statistics, power 28, 90%. So those are the issues we face when we design experiment. Then focus on the data, the input we put in the machine, the model machine, right? So the input is the data quality, right? So that involves pre-processing. Once we have data from the scanner, we go through several steps, right? So we need to take care of slice timing, then we need to adjust the head movement. So that typical one, there's spatial alignment because each individual brain is different, right? How do we compare groups, compare individuals? We need to align individual brain to some standard brain. That's standard brain called a template, standard space. So every brain is transformed into that template. So some regions need non-linear transformation to make bigger or smaller squash. So we need to do that kind of alignment. So that's spatial alignment. There's a spatial smoothing. That's usually two reasons we need to smoothen the data. One reason is because the spatial alignment is not perfect. So that smoothing helps us to sort of improve that alignment to make it blurred. Another reason is to increase the signal to noise. Those are the two reasons. Then there's scanning, right? So the fMRI signal is arbitrary, does not have any unit. Like a length, we have the unit of miles, meter, centimeter, right? But for fMRI signal, the values you get from the scanner doesn't have any physical interpretation. It's arbitrary. The value is usually in the range of like around 2000. But that value does not have a unit. So, but when we say how much the brain, each region in the brain responds to some task, how do we show that the magnitude of response? So that we perform this step called temporal scaling. So then we can interpret the both response in percentage signal change. So that's the reason for temporal scaling part. So we go through those few steps. So those are pre-processing steps. Then probably nowadays people have also recommended to do quality control, right? So you say there's some data really bad, should we remove them? That's called a censor, right? So some data points we want to remove because scanner irregularity, because the scanner has some problems at some particular time points, or due to head motion. If the head moves too much, at some data points, you may want to remove. Those are typical post hoc procedures to remove, to perform that quality control step. Those are necessary, but usually we consider they are beneficial, but sometimes it can be harmful too. How do we balance the two, the trade-off? Even those procedures are nowadays it's just virtualized. It's called pipeline. It's probably each lab has their own specific pipeline. You smooth at 4 millimeters or 5 millimeters. There's no standard. There's no one-size-fits-all procedure, pipeline. But so that's why there's people argue there's a variability. We produce a default because of this. So that's something we talk about later on. So once we have the data ready, we need to fit it into the model. That's what I call data machine. At the individual level, each participant will analyze the data separately. So that's the model usually for task-based analysis. Usually it's a regression model, right? So each voxel have the time series. Suppose we have 300 data points, time points. We put in the model, it's a regression model. Right? So once we have the estimated brain response for each individual participant, then we go to the group level. Suppose we have 50 individuals. How do we summarize those 50 individuals? We say something about the population based on those 50 individuals as representatives. So we want to generalize those samples, those participants, to say something about the general public. So that step is crucial because we want to make a general statement of the whole population. That kind of a model, there are different ways, depends on how simple or how complex your data design, experiment design is. You can maybe do simple t-test, or use a general linear model, or ANOVA, ANCOVA, or even linear mixed effects model, depends on how complicated the experiment design is. Each model, you may also need to consider covariates, right? So males, females, is that you think that's something you need to worry about? Age, brain volume, many things, right? Behavior data, right? So like anxiety, depression, those are behavior measures. Do we want to include those covariates? How do we decide which variables should be included, should be excluded? How do we make that kind of a decision? So there are many things. At the individual level, how do we model the hemodynamic response? That's another complex issue. The typical way, we just assume the so-called canonical curve. That curve is based on some like visual cortex, for example, that's traditional. In the early days, there's a standard curve. So nowadays, people just use that canonical curve and apply it to the whole brain. Any region, regardless, even though that curve probably initially was defined based on either motor cortex or visual cortex, but now everywhere in the brain, we use the same standard curve. And regardless the group, either kids, adults, or old people, right? So we all apply the same curve. So that's just for the simplicity of the approach, but that may cause some problem. But the bigger problem is people call it multiple comparison problem. Suppose we have 200,000 voxels in the brain. Because we analyze each voxel separately, that means we do 200,000 separate tests. So immediately we have, in the traditional statistics, that's the problem called multiple comparison. Some people call it multiple testing problem. And you may say, even if the data is just pure noise, by chance you would get significant results. So that's a big problem for alpha data analysis. So once we have the results at the group level, then how do we report? So because of the multiple comparison problem, so this is like the end product of the machine, right? So people say we need to quality control. How do we control in this case? We need to make the results stringent. How to stringent? Even though at each individual box of the p-value is already below 0.5, but because of multiple comparison problem, that threshold is not stringent enough. So now people need to worry about how to make it more stringent, not just the traditional magic number 0.5. So that stringency is cause a lot of problem. So then there's a trade-off, right? So then there's that customize the results. Anything above the threshold you can report, anything below you cannot. Is that a reasonable approach, right? So then later on I'll talk about that. So big problem. So you can see those 4 components on this slide. Nowadays the pipeline is separate, right? So the person who designed the experiment may not be the same one who analyzes the data, right? So then the point I want to mention here is that because the output, the final you write in the paper is emphasized purely based on the statistic. You don't consider anything else. Don't consider the previous literature, how the brain, whether the clusters in the brain are symmetrical or not. So those kinds of information are not allowed when you perform the thresholding. And simply by controlling the stringency, the end product as a way to filter the results is not a good approach. Maybe we can do something better. Maybe we can argue the model maybe is the problem, not just the multiple comparison. So that's what I want to emphasize. So before I talk about that end product problem, multiple comparison problem, let's just refresh our memory about what you learned in your statistics classes 101. Right? So we're all familiar with this so-called null hypothesis significance testing. Right? So whenever we have a statistical model, we end up with something we want to see about whatever we want to compare, association, right? So the data coefficient evaluation model. We pretend there's no effect. So that's why it's called null hypothesis. Whenever like you compare 2 conditions or compare patients versus controls, we pretend that there's no difference. So that's called null because it's 0, right? It's 0 effect. So the brain region is not involved in this task, or there's no difference between such and such. So that's called null hypothesis, 0 effect. So once under that condition, now we want to check our data. Of course, the data, some regions in the brain, maybe the evidence is strong or maybe weak. We may surprise because that we pretend there's no effect. The data shows it contradictory to that null hypothesis. So that's how surprised we are is measured by that p-value. Smaller the p-value, that means we are more surprised. So the p-value measures how contradictory of the data against the null hypothesis. So the 0 effect. So there is a threshold, that threshold called a significance level, that's called alpha. The alpha usually, as for some reason, it's 0.05. It's peaked alpha about 100 years ago by Fisher, right? So the famous statistician, 0.05, simply because that's magic number is 1 over 20, right? So nowadays we are all stuck with that number, 0.05. But we can criticize that approach from many perspectives. Right? So there is a famous saying, God loves 0.06 almost as much as 0.05. We argue, why do we pick up 0.05? Is anything wrong with 0.06 or 0.055? I mean, or 0.04? We can argue that for many hours, right? But so that's arbitrary. It's too arbitrary. That's one problem. Second problem is we have fully ignored the type 2 error. The type 1 error is called false positive. That's the alpha 0.05. If we look at the matrix on the lower right corner, right? So there's 2 by 2. So there's two. Why is it 2 by 2? Suppose there's this two columns correspond to the null hypothesis. Null hypothesis is true, that means zero effect. The second column is for the null hypothesis is false. So then we need to make a decision, right? So those are the two rows. The first row is we believe the null hypothesis is false, so we check the null hypothesis. The second row is accept, right? We don't, we check the null hypothesis. So that's why 2 by 2. So the diagonal ones, the two red ones, we make a mistake. So the upper left one, let's put a type 1 arrow. The lower right corner one, that red one is the type 2 arrow. The type 1 arrow, we only focus on the traditional statistic. The typical one focus on type 1 arrow because we are worried about there's no effect. We make a decision, we claim there is effect. That's horrible for us, for science, right? So there's nothing, we claim there's something that's a terrible situation, so we want to avoid that. That's why the traditional studies focus on type 1 error. But there's a type 2 error, right, too. That means there is something, but we fail to reject that. So we miss that opportunity to detect that effect. So the traditional studies, the larva significance testing in common practice, fully ignore the type 2 error, right? So that's the sensitivity problem. Of course, there's the third issue is that once we dichotomize, then this decision process will fully ignore other evidence. Like in the brain regions, we already know some regions based on previous literature or the symmetry, there's other piece of information we can utilize, as I show later on. So let me demonstrate another problem. If we solely rely on p-value. So look at the left plot. So there are blue one and red one. The blue one, if we focus on the p-value, 0.02, the red one, the p-value is 0.09. So you would think, if we just focus on the p-value itself, the blue one would survive our threshold strategy, right? So we would say, consider that effect is significant. The red one is 0.09, one tail. And it would fail to pass our filter process. Doesn't mean if we do that, that doesn't mean the red one has smaller effect. In this case, it's totally the opposite. Most of the time, the red one, the B effect is larger than the blue one. So that means big problem. If we simply based on p-value itself, we're going to make such a big mistake. We claim the A effect is bigger than simply based on p-value. We survive the threshold, right? So that's one scenario. On the right-hand side, the two effects have exactly the same p-value. Does it mean they have the equal effect size? Well, you can tell by their distribution. So most of the time, even though their p-value is the same, but the orange curve C, most of the time is greater than the blue curve. So we cannot simply based on the p-value make our decision. And for alpha map, this is especially problematic because if you read the paper, they don't talk about effect magnitude. The color bias, most of the time, it's just the t statistic, z statistic, or p-value. They don't show how much the brain responds at each brain region. They don't tell you it's 1% single change or 0.5. They don't show that. That's because in the field, the current situation is the opposition with statistic values. So maybe we can do something better. That's a different perspective. So instead of focus on statistic p-value evidence, we can also change our focus on estimation. By estimation, we can estimate the magnitude like those curves show in those plots. Even though in brain region it's hard to show the distribution, at least we can show something. That is something, one thing we can show the point estimate, we can show the uncertainty. Uncertainty can be standard error, or can be some uncertainty interval. For example, traditional 95% confidence interval, right? So we can do that. That's much better. Right? We also can utilize the prior knowledge, which I will demonstrate later. But now let's look at a sort of a concrete example without reporting. Suppose this is a brain one slice. This you would typically see in the publication, right? You say the brain slice, they show those are the clusters that survive the currently standard of threshold after multiple comparison correction. I don't even want to call it correction, it's just an adjustment. Because how correct it is, that step is something we can argue. So let's you would say it like this, because those are the so-called clusters that can pass that is surviving criteria, and the color bar is usually the statistic value. Once we say this, well, you say that the brain is so clean, right? It's only those regions are involved in this particular task. Actually, this is the contrast between two task conditions. It's an incongruent versus congruent. It's a flanker task. So immediately you may say, is really the brain that clean? I mean, it's only those regions are involved. That's the first question. Second question, looks like there's some asymmetry. So some regions, for example, here, this cluster here, but on the left-hand side, we don't see it. Is it really true the brain behaves in that bilateral asymmetry? Right? So is it really the case? Well, we don't know unless we show the full results. So that's question, right? So those are the fundamental problems. So is it really, when we have the results, it's really a decision-making process? Do have to make a decision. That's the first problem. I mean, in real life, we do have to make a decision. For example, we review a paper, research paper, the reviewers have to make a decision whether I would give a chance, second chance to revise the paper or totally just reject. So that's a decision process. Drunk driving, we have to put a threshold there. But for research, do we have to put a threshold? If we do, does that threshold make sense? Right? So those are the problems. But more fundamentally is the modeling approach. Actually, not just the controlling and the product. It's the modeling part is problematic. Why? Think about it. How do we analyze the brain image data? Suppose we have 200,000 boxes in the brain. We adopt this approach called the massive univariate approach. In that, we just analyze each box separately, right? So we assume all those boxes have no relationship. Each box is behave, we assume they behave independently with all the other boxes. That's the approach. That's why we have multiple comparison problem. In the end, we have to take care of that. So that's the fundamental issue. So if we see this model, suppose we have 200,000 voxels. Suppose this is a group that will have a simple regression model, right? So Y is brain response at each voxel, the first voxel. The X is suppose some behavior lesion, right? So in this case, the brain response is associated with, for example, anxiety. Each participant has an anxiety measure. So we build this simple regression model at each voxel separately, right? So that's end up with 200,000 separate models. Those 200,000 models, they don't talk to each other, right? So they're totally embedded. That's why we have multiple comparison problem, right? So then if you're familiar with the steps, the three major approaches to handle multiple concern problems: one field theory, Monte simulations, and permutations. We don't want to go into details. But the fundamental problem is this. Because we assume all the voxels, we have no prior knowledge about their relationship. So that's why we assume it's a uniform distribution. So this horizontal line. When we build a model, we have no knowledge. It can be the effect, can be anywhere from -infinity to positive infinity. That's the underlying assumption. In fMRI, that's everybody does. But in reality, is that true? Well, if next time when you analyze your data, you can plot out those voxel values. If you look at, you would be most likely like the one on the right-hand side. You would be centralized around some value. Most of them come close to 0, and 10% off on both ends. If you don't believe me, try yourself next time. If you find something more closer to the left-hand side, tell me. That would be something problematic with your data. So most likely, the data would behave like a centralized distribution. So that is important for us because when we build a model, use the traditional approach, massive univariate modeling, we make this assumption on the left-hand side as uniform distribution. We have no prior knowledge, but that's not true. So it's more reasonable to make an assumption like Gaussian distribution, some centralized distribution. Does not have to be Gaussian distribution, but it's something like that. That information, if we don't use that, immediately we have trouble. That's why the current approach, the multiple comparison, so-called correction, is problematic because the penalty is just too heavy because we don't utilize or don't take advantage of this distribution information. That information is not in the model building process. So that's why the penalty, the so-called multiple comparison correction, whatever approach you use, the finding-wise error is just too penalizing. So it's excessive. So that's why, even though you may think the cluster level p-value is 0.5 sounds like reasonable, but in reality, this is too heavy, the penalty. So if we show the full results, this is not even full results. This we put a highlight, but only high. So we apply some soft thresholding. Below the threshold, we don't hide it. Instead, we temper it off, fade it off gradually. So now immediately you see this image versus the left one. Which one, first of all, which one you think is more reasonable and gives you more information? Immediately say symmetric, right? Symmetry. So even like they are blue on both sides, on the left hand, it's hidden. But on the right hand side, you may argue maybe that's just pure noise, but at least that anatomical information, the symmetry information, give us some extra, right, confidence. Even though the statistical evidence, maybe you consider it's too weak, but still that extra information boosts up our confidence, right? So you don't have to report, at least you don't have to hide it, right? So this is, I think it's a better approach. So this I call it solution one. We still adopt the traditional approach. Analyze each box separately, but don't be too obsessed with the multiple comparison or adjustment, right? So don't trust, think about the cluster boundary. Does the boundary mean anything neurologically? That boundary, each cluster may cover multiple regions, part of each region, not for each region. If we stick to the traditional statistic, if one cluster covers part of a region, does that mean we think that region only partially activated? Is that really the case? Can we even talk about that? But in the discussion, the methods paper discussion, people don't describe that way. Instead, the peak of the peak voxel to represent the whole cluster. Even though that cluster may only cover part of the region, they still talk about the whole region. So there's a lot of inconsistency in model 2. Well, some people still like the cluster boundary. You can overlap the two, right? So maybe I can demonstrate it. I thought I could, well, maybe just give up. So since I can't get out of the slide, get out of the slide, go to the terminal, show they are using the ethnic GUI to show how to present the display approach is a highlight but don't hide, how to fade away. Right. So that's the first solution. Oops. All right, let me quickly go here. So the second solution, we don't control the end product because the woody problem is the model itself. not about the end product, the statistical results. How do we directly go to the root cause? That is the model, the massive unifier approach, right? So those are the voxel level approach. Instead, we build one model because we only have one brain. The brain is just one organ. The information flow should be shared, right? So that's why we can adopt this called a hierarchical approach. Because I already showed you previously, we assume the brain across different brain regions, voxels, they should follow some centralized distribution. We can take advantage of that. So don't pretend all those voxels, all the brain regions are isolated, disconnected with each other. No, that's not the case. We should take that information into the model. That model is a hierarchical model. The cross-brain information, that distribution, is incorporated into this one single model. If we do that, now when we have one model, there's no multiple comparison issue. So immediately that we gain some, we don't have the to that penalty step. So let me demonstrate one particular example. So that's 124 individuals, right? So the traditional approach, you do the whole brain, then perform multiple comparison correction, only 2 clusters that are lucky to survive. But if we build one model, in this case, I'm not doing at the voxel level, instead I extract 21 regions in the brain. So if I use this approach, I solve it instead of using the traditional statistic, using Bayesian approach, you can say those 21 regions, I show the posterior distribution. So the vertical line, the green vertical line is the 0 value, so there, you can say probably at least 1/3 of the brain regions are on the right-hand side, mostly are on the right side of the vertical line. So we have confidence to clear probably like 8 or 9 regions. We have pretty much solid evidence to support the whatever the effect we are estimating, instead of just 2 clusters with the traditional approach. So this is because we build one single model to handle all the 21 regions. So that's one issue. We don't control the end product. Instead, we improve our modeling approach. The next topic I want to talk about also another aspect in model building is the covariance selection. Right? So there are many variables we can think about. Gender, right? Age, brain volume, handling needs, right? Left-handed versus right-handed. There's so many variables. Which variables should we consider? Should we consider all the variables that we have data available? Right? So that's the issue here. Traditional approach would based on p-value, based on model comparison to step up, step down, like calculate the R-squared determination coefficient to determine how important each variable is. Then we decide that variable is worthwhile to put into the model. That is not a good approach. So the good approach is based on the relationships among those variables. That's an important one. Let me use a concrete example. This is not FRMI, it's a structural FRMI, right? So DTI, for example. So in this case, we have the Y, the response variable or outcome variable is short-term memory, it's a behavior, it's a score, right? So it's a value. Each individual will have a value. Then we have the predictor. Predictor is the gray matter density. That's like the voxel level in the brain. So each individual has the voxel value, that's the gray matter density. We have, let's consider 5 covariates. So we have males and females, 6, that's one. That's a between individual grouping variable. Then we have the genotype, that's another between individual variable, right? So those are 2 factors. There are 3 quantity variables, age. Then we have body weight. Then we have into quantity volume, how big the brain is, the brain size inside the skull. So those are the 5 variables. So now I raise 4 questions. Think about the Y. Y is behavior, is 1 number per individual. But the X, the gray matter density is our experimental variable, is many voxels, 200,000 voxels, we have 200,000 gray matter density value. So the your image data, software packaging, usually the Y is the box value, X is some single number, right? So in this case, the software is a little bit slightly designed to the Y is just a single number. Can we switch X and Y? So that's my first question. Second question, we have 5 covariates. Right? In addition to the grammar density, we have 5 extra covariates. Is it okay to include all of them? If not okay, how do we make that decision? The third question, if we include all the covariates, can we report those regression coefficients, those beta values? Is it okay to report them? That sounds strange, right? So whenever we have the model, we have the beta values, we can report all of them. So that's my third question. Last question, suppose we can, in the future, we will think about this experiment, should we include more covariates, right? How do we decide which variables are worth to spend resources to collect the data? For example, body height, should we include that? Or the sleep, how many hours each individual slept during the previous life? That may have some impact on the memory, right? So that's something we need to take into consideration. How do we make a decision? So there's a new science called causal relationship, causal inference. Let's look at the first graph. We draw the relationship based on their relationships. Suppose we consider a simple one. Look at the weight, how the height influences the weight, right? So that's relationship. But then there's a males and females sex. This relationship, I mean, intuitively, males and females influence both the height and the weight. So that's called a confounder because it influences both the predictor and the response variable. So that's, some people call it a fork because the shape is a fork. So that's called a confounder. The middle one. So this, in this case, we compare males and females in body height. In this case, it's called a collider because if you look at the relationship, the weight is both the X and Y influences body weight. So in this case, it's a collider. The last case is now we compare the body weight between males and females. Now the height is, the relationship changes now because the height is called a mediator. If you look at the relationship, because the information flow from X to Y, there's one path, second path is from sex to height, then to weight. So if we only focus on 3 variables, they have those 3 relationships. Depends on which relationship we have, then we can make a decision then whether we should include that variable as a covariate or not. The first case, yes, we should, because it's a confounder, because the causal relationship of height influences weight is confounded by males and females. That makes intuitive sense. In that case, we should include sex as a covariate. The second case, what do you think of the second case? Should we include weight as a covariate when we compare body height between males and females? What do you think, based on your intuition? Yes? Raise your hand if you say yes. No? Everybody think we should not? In this case, we should, absolutely we should not, because it's a confounder, because there's a reason you can want simulations to verify, because there are so many, even during the pandemic, the COVID, some papers published, the epidemic papers, make a big mistake because of this confounder effect. Not about this, but COVID versus hospitalization. When you have another situation, like for example smoking or other disease, then if you're not careful, you may have this confounder effect. Then you may make a spurious discovery. So that happens quite often actually in English. The last case is called mediation. This case is probably the most tricky part. It's sometimes you may want to include value as a covariate, sometimes you don't. Depends on the situation. So depends on what you focus on. If you want to focus on total effect, then we should not include the mediator as a covariate. If you want to estimate the direct effect, then we should. If you're familiar with some, I don't know, social science, psychology, people do mediation analysis. That's why this case is very tricky. So those are the basic types, 3 types. It's easy. But then there's other 4 scenarios like this. It's just simple. It's just the covariate inference is just 1, right? So the first case is called is the child of the predictor. The second case is the child of the response variable. The third case is the parent of the predictor. The last case is the parent of the response variable. So there are 4 different scenarios. Only the last one is good idea to include as a covariate. The other 3 cases we should not. So we don't have time to discuss the reason, but that is. So let's look at a simple case. Suppose for neuroimaging, right? So suppose we have alpha data. We have males and females, we compare their brain response. We have age as a potential covariate. Is it worthwhile, is it a good idea to include age as a covariate? Well, let's make an assumption. Suppose males and females, when we recruit those participants, they're balanced, they have roughly the same average age. So if you think about that case, the age probably is reasonable to assume influences both response, but doesn't influence whether the person is a male or female, right? So that, of course, there's no relationship. As long as the balanced, when we recruit those individuals, participants, their age is balanced. So this is a parent of the response variable. So it is a good idea to include age as a covariate, but it's not absolutely necessary, but it is a good idea. So how about this head size? This alpha cell, they have this measure called the brain volume, right? So it's a popular one. If you read the literature, so many papers published with the head size as a covariate. Suppose we want to compare brain response, males and females. It is a good idea to include head size as a covariate, right? There are 2 possibilities. Either, well, we already know males and females on average, they have males usually on average, not individual level. On average, males have a bigger head size. Okay, that's just a fact. So it's a child of the predictor. Do we know head size influences both response? Maybe, maybe not. We don't know. Either way, we have those 2 cases, right? So the first case is a child of the predictor. In that case, we should not. That if we do that, that's going to mess up. It's going to create a bias estimate. The second case is the mediator. Mediator, if we focus on the total effect, still it's not. We should not include the head size as a covariate. So either way, it's not a good idea to include the head size as a covariate, even though it's a popular covariate in fMRI literature. So there are many cases. I'm going to skip the cases. I'm running out of time. So so this is the example I earlier showed you that there was those are 5 covariates. So we just draw this. People call it bag, right? There's a causal relationship among those variables. How do we know the relationship? This is nothing about statistics. This is about your domain knowledge. As a researcher, investigator, you are supposed to know their relationship, right? So most of the time, we do have that prior knowledge. For example, age. We know age influences brain matter density, right? So as a person becomes older and older, the density in the brain changes. Short-term memory, that's a behavior. How much we memorize it, of course, it becomes older, memory deteriorates. So we know age is a confounder, right? So we go through that process for all the covariates. Then we draw this map to this diagram. Once I have this diagram, then we can answer those 4 questions. Is it a good idea to switch X and Y? No, because the causal relationship, the brain matter density influences the short-term memory behavior. the behavior doesn't influence the gray matter density. So we should not switch the X and Y. The second question, should we include all the covariates? No, some of them is not worth, should not. For example, ICV, intracranial volume, that is only influence the gray matter density, it only influences the X, it does not influence Y. We cannot go from this which to Y, except through gray matter density. So that's a parent of a predictor, and we should not include that as a comparator. Same thing with weight. The weight is basically all the information flow there stops. It doesn't go to the X, gray matter density, it doesn't go to short-term memory, so the weight should not be included. So those two covariates, intracranial volume, ICV, and body weight should not be included. So when we look back, we should not even spending our time and resources to collect the data for those two variables. So it's a waste of our resources. So only three covariates we should include: age, sex, and the genotype, ApoE genotype. So those covariates we should include. Others, no. So that answered the second question. The third question, are all the estimated effects interpretable, or should we report all the beta values, in this case age, sex, and ApoE genotype? Well, you think if there's a model, why the model have output? Why cannot we report all the output? So the products, right, from the same machine. Well, the question is, if we switch, for example, think about the age influence, that effect on short-term memory, we need to change the diagram. Then the other variable the relation would change, right? We need to think about the gray matter density is what? In that case, it's a mediator. So whenever we change our focus, we need to consider the total of the relationships also changed. Then we need to make a decision, all the other variables should be included or not. So each time we build a model, that model should pivot around one particular focus. Once we change our focus, the model may need to be changed as well. So that's important. We cannot just say we have a model, we can report everything from that model. No, that's not a good idea, even though that is a common practice, regardless in FMI, even in social science and in other fields, psychology. People do that on a daily basis, just report all the results from there's called a table 2 paradox is to describe this problem. All right, so to summarize, how do we choose covariates? We did based on their causal relationships. That causal relationship does not come from the model itself, it comes from the investigator and the analysis. We know that from our domain knowledge. So that's always we say science before statistics. So always the science informs the model building process. We should not let the model to decide the science. It's always the science before the statistics. And usually, of course, the statisticians are happy, or they can rule the world. They can determine how you can report it, how you build the model. No, you should take the steering wheel. You should make that a decision what model you want to build, and also take care of the output, not just purely based on statistics. So draw that diagram, build the model, then report it wisely the results. I'm going to skip this HRF stuff. There's also Wilson state, even more problems with Wilson state. I think I'm going to skip that. Let's just want to summarize. Summarize FMI, right? So in this talk, I focus on 4 components: experiment design, pre-processing, modeling, and reporting results, right? Result reporting, those are the 4 components. Experiment design, I mean, it's it's usually even, yesterday I saw somebody asked me about how to analyze data. Well, there's some issues. That issues boils down, basically it's a design problem. Didn't design the experiment properly and cause some issue at a later stage. It's difficult to retrospectively to fix. The model cannot solve the problem. Instead, it's a design. So you either design that proactively prevent some potential problems at later stages. So the experiment design is very crucial. So those sample sizes, right? Not just the participants. The number of trials is also important. That is usually ignored. People always think about the number of participants. The number of trials is almost equally important. So that's, I don't have time to discuss that, but so that you need to focus on randomization. So you need to recruit those participants randomly from the population. Don't focus on particular one. Especially like you focus on the college students on the campus, that's probably a little bit biased to some extent, not representative to the whole population. So try to avoid that problem. Jittering, you randomize and jittering the two separate conditions of trials, neighboring trials, you only vary the intervals. Right? So the scanning parameters we do about head motion is a big problem. Head motion is always a big problem. There's no easy solution. Even if we do, there's procedure per process step. There's a quality control. Those are just, when we look back, try to fix as much as possible. The better idea is try to avoid during the scan, try to reduce the problem. Right? So there are many proactive procedures to do that. Covariates, of course, when you design experiment, think about what covariates you want to put in the model. You need to collect the data at that stage. Don't want to think about the covariates when you build a model. That's already too late, as I demonstrated with that motivation example. Pre-processing is a mess. It is a mess. There's no, that's when people talk about the reproducibility, pipeline variability, it's because there's no simple, one so-called standard way to pre-process data. Why? Because there's a benefits, it's necessary, but also may do harms. We don't know, nobody knows what kind of harms. At least conceptually, we do know that some steps are harmful, but also beneficial. We cannot separate the two, the problem is. And we don't know which is, whether the benefits outweighs the harms, we don't know, nobody knows. Modeling, there are many issues, right? So there's a, should we assume the canonical curve? We already know that's problematic. That's not representative to the whole rate. So we should avoid that, adopt the estimation instead of canonical curve. Data hierarchies, we talk about one particular across the brain. There's a hierarchy structure, that's a centralized distribution. We should take advantage of that, put it into the model, instead of pretend there's no information sharing across the brain. That's just not in the real situation. Covariates are important, not just let the model decide how important each variable are. Instead, use your prior knowledge to draw the causal relationships. You take the steering wheel, don't let the tail wag the dog. That's just not the proper way to do statistics. Without reporting, try to report the full results as much as possible. Right? Focus on estimation, not the decision-making process. Science is about the accumulation, knowledge accumulation. It's not about each study is not decisive. If it is decisive, we will not have to repeat the experiment, right, from across different labs. So that's why we need to maintain as much information as possible. Don't treat it as a decision-making process. Treat it as accumulation, knowledge accumulation. So that's why it's important to make it transparent, right? Nowadays, we emphasize open science. So report full results, only hide the results is part of the transparency process. With that, I think I'm done with this talk. Thank you. Happy to answer any questions or comments.
will be your take-home message, like how to minimize information waste? Should we use less contrast? Should we increase number of trials? Or every experiment is different? Is there a certain pathway you would suggest us to minimize the waste?
Probably, I guess the last slide, to some extent, probably answer is just one. It's not just one simple aspect.
Yeah.
Right? So, and also each individual study is some unique part, like a covariance.
Yes.
Or you want to focus on some brain regions. You want to focus on visual cortex. You want to focus on emotion or amygdala, those are small region, right? So that may changes your even scanning parameters too.
Yeah.
So there are many aspects. This slide just talk about some general. For my skill, I think there's a lot of room for improvement. There are many issues I didn't even cover, like body signal itself. Body signal is not about neural activity. Even though we treat it as a proxy, there's a gap. Because body signal measures the oxygenation, how much blood flow it is. Think about some tasks. May trigger neural activity, that we say then blood flow changing. That's perfect. However, it maybe triggers both neural activity and physiological, or for example, some drugs may change blood pressure. That may cause the blood flow change. That may mixture of, sometimes the body signal may be purely due to physiological components, has nothing to do with neural activity. In that case, it's difficult to make, provide evidence purely based on fMRI. We may need something else, for example, ASL or EEG, because they are more focused on something else to complement the fMRI discovery.
But there are things we can change, like experimental design, as you mentioned, like number of trials is as important as number of subjects.
Right. Yeah.
So would you suggest us to have less number of contrast and more number of trials in a given time? Would that help us to manage?
Well, purely based on statistics, number of trials and number of participants are roughly equal. Suppose you want 50 participants, 50 trials. So that it's a hyperbolic relationship. By that I mean 50 by 50, 50 participants, 50 trials, the product is 2,500. So that's one way. Or you can switch to 40 participants, 60 trials, the product is 2,400, roughly the same. Or you can switch 60 participants, 40 trials, or you may increase the trials 100 participants, 25 trials. So all those pairs are roughly the same. The end result is roughly the same.
Assuming the variability across subject versus variability across trials is kind of equal, or
that's another point. But let me come to that later.
Yeah.
So suppose that's the case, you may choose any of them. They're roughly equally efficient.
Yeah.
But you can make a decision which is more more efficient,
yeah.
or more the participant tolerance in the scanner, right? So that you have to consider those practical issues. Come back to that, you raise that question. Cross trial variability was individual variability. That is something very interesting and intriguing too. I don't have an answer, but based on my empirical evidence, cross-trial variability is way much larger than cross-individual variability. You may think individual differences, right, even few of us, we are so different. By our appearance, by brain response, you may think would be quite different. Even the same brain, my brain, if we repeat 50 trials, those 50 trials varies, right? But that variability is greater than the variability among us. Why? That's something probably more fundamental about our brain. I don't have a clear answer. I do have others, but that's probably a long story, but we can talk about it another time. But that is something intriguing. It says something about our brain. Why even the same task, our brain responds differently. It's exactly the same task. Even simple tasks like push a button, right? It's simple each time, just push a button. Suppose we do that, repeat that 50 trials, we focus on one particular brain region, the body response is quite different from trial to trial. That says something about your brain. That's because we measure about the blood flow. First of all, it's not excited about the neural activity. That's one thing. Even if it's about the neural activity, there's something else in the play. It's not just that the external, there's something in the brain. It's just not like an engine idling. It's more like the waves in the ocean, right? So the brain is not idling. It has its internal dynamics. So that's my hypothesis. Anyway, I digress. Right. All right, I think no more questions. I think that's it. Should we start recording here?